Hi, this is Lisa Knight, and I am going to go over Lab 2, Part 2, Analyzing the Free Fall Motion of Objects. So in this particular lab, you're going to you have a choice of looking at any of these objects that are tossed upwards and experiencing free fall, which means that the only force acting on them is the force of their weight, which causes them to slow down and speed up by 9.8 or 98 centimeters every second. I turned on the ruler and I turned on the stopwatch, and that way I could stop this every 0.05 seconds and take a reading of where it was at every instant. And so I would just pick one point, one side of the object, like I chose the top point of the ball to measure at every instant. I've done this for the large ball and for styrofoam ball. So these are the heights of the large ball and the styrofoam ball here. I also have the velocities, which we'll talk about in a minute. And I recorded all that information. And I configured my graph to show me the height of the large ball versus the time of the ball on the x-axis. And when you look at that, it makes sense that this should not be linear. It should not be linear because slope of a position graph is velocity. And these balls are not traveling in the same direction or at the same speed every instant in time. So they are not experiencing constant velocity. They are changing their velocity every instant in time by negative 98 centimeters per second every second. So when I graph this, I should expect to do a parabolic curve fit. And if you look at this, what are these little coefficients? Well, A actually corresponds to one of our kinematics equations. It's 1/2 of time squared plus the initial velocity times time plus the initial position of the ball. So A should be half of gravity, and it is. And B should be the initial velocity of the ball, which was about 343 centimeters per second. And C should be about where it started. And at that particular time that I started, it was at negative 60 centimeters below the reference point. So the position time graph is the slope of that tells you whether or not the object is traveling at constant velocity or whether its velocity is changing and it is experiencing acceleration. So in this particular example, the slope gets steep, starts out pretty steep and gets flatter and flatter and flatter. At the very top, the slope is 0, and then it gets steeper and steeper and steeper in the down direction. So it's slowing down to 0 and then picking up speed in the down direction as it falls. So it is accelerating. Now, what you're going to do is you're going to find the velocity of the ball at each instant in time. And to do that, you're going to find the slope. Instantaneous velocity is the slope at an instant on the position graph. So to do that, I'm going to change this curve fit to a line. Now, that line is being taken between the average of all these points. So what I'm going to do is I'm just going to click on these points and turn them off out of the fit. And if I keep just clicking on them like so, you see I start to approach finding, let me get this one off, the slope at every instant. So if I just want the slope here, I want to find the slope as close as I can at every instant. So for example, the slope at the top here is 0. That would be the slope at the very top, which is at 0.35 seconds. Okay, at 0.3 though, I want to get rid of that. So at 0.3, There we go. Right here, I have negative 1.2 centimeters. And I can keep doing this. So I want to find the slope at a point. So here's a slope at a point here. If I want to find, and this point is at 0.3, so it's negative 2.066. And then if I come over here, excuse me, I'm sorry, the slope is 50. I'm going to read my slope off of my equation of that line. So you're going to find the slope at a point, at each point. So you're going to start with the slope at the very first point, the second point, and so forth. And you're going to have to kind of play around with that. It's a little tedious, but you can do it. Once you get that, then you can tell it to graph on the y-axis the velocity. So now if it's changing its speed by the same amount every instant in time, 9.8 meters per second every second, or 980 centimeters per second every second, you should expect it to go down by the same amount, approach zero at that instant, and then get faster by the same amount every instant in time. And you will do a curve fit that's linear, and look, I got 960 centimeters per second. So when you start answering these questions, they're asking you, what is the slope of the line? Well, your equation tells you that, and its units are in centimeters per second squared. So that tells you, because the slope of a velocity time graph is acceleration, and the slope is a constant, negative 960 centimeters per second squared. So that tells you that it is constantly accelerating, just like the position graph told us that in a different way. The y-intercept here, if you think about it, this is a velocity graph. So if I look at where it hits the velocity graph, it's telling me that its initial speed was 338 centimeters per second. And when I describe the equation of this, I would say that y would be the velocity is equal to the acceleration times time plus the initial velocity. So that's also one of our kinematics equations. The other question it asks you about is, what is its velocity and its acceleration at the height? Well, its acceleration at the top point is the slope of this line. The acceleration is never zero, because this is an average zero. Never stops accelerating, it just stops physically for an instant in time. So Vy will be zero at the top, but A will continue to be 960 centimeters per second every second in the down direction. All right. Good luck, guys.